let's move on to the final talk of this,
thanks.
this session. Thank you. So, been Intae Jung talking about boosted Lyman-alpha transmission of IGM in UV bright galaxies. Please go ahead and share the screen. All right.
Hello, do you see my screen?
Yeah, please, go ahead.
Yeah. Yeah, hi everyone. I am Intae Jung, a postdoctoral fellow at NASA Goddard. Today I'm going to talk about boosted Lyman-alpha transmission of the intergalactic medium in UV bright galaxies. In the previous sessions in this SAZERAC conference, there were lots of great talks already on Lyman-alpha during the epoch of reionization. Then here I'm presenting my work also on Lyman-alpha during the epoch of reionization, but more focused on its inhomogeneity and galaxy UV magnitude dependent Lyman-alpha transmission in intergalactic medium. So for this work, I'm work with the clear collaboration team with the listed core members here. And there were numerous talks on Lyman-alpha, so I'm not going to give too much of an introduction, but briefly remind you. So the Lyman-alpha is sensitive to the amount of neutral hydrogen. So the evolution of Lyman-alpha visibility has been used to trace the evolution of neutral hydrogen of the IGM during the epoch of reionization. Particularly, I'm here more focusing on the distribution of Lyman-alpha equivalent width in my previous Lyman-alpha studies on the right panel. As this analysis of Lyman-alpha equivalent width uses more observables than the Lyman-alpha fraction, such as Lyman-alpha flux and galaxy UV magnitude. The Lyman-alpha equivalent width distribution is often described in exponentially decaying functional form with the characteristic e-folding scale W naught here. So the characteristic value of W naught represents the Lyman-alpha strength statistically. So in short, in the bottom figure, I'm showing the evolution of equivalent width distribution from my previous study, which also suggests reduced Lyman-alpha equivalent width during the epoch of reionization at redshift of 6. However, the recent Lyman-alpha studies suggest a very complicated picture of reionization. So, for example, on the left panel, I'm showing the neutral fraction measurements of the intergalactic medium from various works. The focusing here at redshifts 7 to 8, these Lyman-alpha studies, including the measurements from my recent publication, show disagreements between their measurements. Furthermore, a set of quasars Lyman-alpha damping wing analysis provided a large scale of IGM neutral fraction at redshift above 7 from their quasar observations. Such a disagreement between the IGM neutral fraction measurements directly suggests the IGM did not occur spatially uniformly, but in an inhomogeneous way. So in the same context, the various observational studies of Lyman-alpha emission have provided an increasing body of evidence for inhomogeneous reionization caused by individual or groups of bright galaxies in the middle phase of reionization. So for instance, the recent findings of clusters Lyman-alpha emitters at redshift 7.7 from Tilby et al., and also a protocluster structure of Lyman-alpha emitters at redshift around 7, just presented by Wei Hu. Additionally, a highly ionized structure with 4 clustered Lyman-alpha emitters at redshift around 7.5 from my recent study suggests enhanced Lyman-alpha visibility from these bright galaxies. So, and beside these studies, we have noticed numerous other studies presented in this conference provide increasing body of evidence of ionizing bubble structures from Lyman-alpha observations, particularly from bright galaxies. All of these suggest on accelerated reionization nearby these clustered brightest galaxies. Being motivated by these recent findings, we attempt to conduct statistical analysis of Lyman-alpha equivalent with distribution, which is dependent on galaxy UV brightness. So in order to do that, we utilize a spectroscopic dataset of HST slitless grism survey called CLEAR. The CLEAR is the CANDELS Lyman-alpha Emission at Reionization Experiment, is the cycle 23 HST observing program. The PI is Keck Popovich at Texas A&M, and the CLEAR observes the 12 fields in CANDELS GOODS field, as shown in these figures, to 10 to 12 orbit depths with the G102 grism and the HST WFC3 camera. So in short, we extract the clear grism spectra of around 100 redshift 6 to 8 candidate galaxies from this data set. So the photometric galaxy selection is based on the Finkelstein et al. 2015, and the spectral extraction was done with Grizzly. And we thoroughly performed the inspection on emission line and continuum detection candidate, but unfortunately, we do not find any of these new detections from CLEAR. So lastly, we cleaned out contamination sources carefully based on the multiple PA position angle observation data. This resulted in HST grism spectra of around 100 redshift 6 to 8 candidate galaxies. Those are non-detections though. The CLEAR provide a wide dynamic range of galaxy UV magnitude compared to other targeted ground-based observations that is blind, because it is blind survey. However, what it can do with non-detection only is just providing upper limit of the Lyman-alpha equivalent distribution. So we thought better combine these CLEAR data set to the existing deep Keck observations. So those are denoted as the cyan and yellow rectangles here, which are DEIMOS and MOSFIRE observation pointings in the GOODS field, and that are published in my previous papers. And those Keck dataset provide the spectroscopic dataset of additional 100 redshift 6 to 8 candidate galaxies with 13 spectroscopically confirmed Lyman-alpha emitters. As a result, we comprised HST plus Keck dataset of over 200 redshift 6 to 8 candidate galaxies in order to explore the MUV dependency of Lyman-alpha equivalent distribution and the Lyman-alpha IGM transmission at redshift of 6. In the left panel, it shows the MUV distribution of sample galaxies in CLEAR as a function of redshifts with Keck targets and M star MUV relation shown in the right panel. So all CLEAR targets are shown open circles, and the Keck targets are shown the fields blue and red circles. A wide dynamic range of UV magnitude from CLEAR sample apparently shows unbiased nature of the blind survey compared to the targeted Keck observations, including UV faint sources. And I'm going to touch a bit of details how I can constrain the Lyman-alpha equivalent distribution with a tinish number of Lyman-alpha detections with a bunch of non-detections. So we introduced the methodology for constraining distribution by simulating the expected number of detections, which considers data incompleteness of observations. First, photometric-redshift uncertainties and galaxy UV continuum level, and also observing conditions. Briefly, with the simulated Lyman-alpha emission lines per individual targets, we assess the likelihood of detecting Lyman-alpha emission lines as a function of their detected signal-to-noise levels. And we fit the simulated template to our actually detected Lyman-alpha lines. So the red lines are actually detected Lyman-alpha lines from our observation. So this is for finding the best fit evolving scale, which is to reproduce the detected Lyman-alpha lines. The strong advantage of this method is that in addition to our positive detection of Lyman-alpha emission lines, our non-detections are highly constraining as well in the simulation step. So we applied this methodology to our clear data set as well. So here I'm going to show how much we can be benefited from including non-detections in this analysis. So in the top left, I'm showing the Lyman-alpha detection limit in terms of Lyman-alpha flux and rest to equivalent width that are measured from individual clear spectra. And on the right panel, the figure shows a simulation exercise on how the measurement of e-folding scale would be changed with including additional non-detections. So x-axis shows the multiplied number of non-detections to the original data set. So if you have non-detections, which is doubled, there are third data point here from the original, the first data point, the constrained e-folding scale is reduced and constrained with smaller error bars. So, and at the bottom, I'm showing the actual update with additional clear data set with existing Keck data set. The bottom left shows the result from my previous publication, which is based on the Keck MOSFIRE data only. The data point at 6.5, that is from DEIMOS data set, and 7.6 from MOSFIRE data. And now, including 100 non-detections from clear, update these measurements as shown the purple data point here that are slightly reduced and with smaller uncertainties. Now here I'm showing a key result of this study. So there are about Lyman-alpha equivalent width distribution and the IGM transmission depending on UV magnitudes. So in my previous paper, Jung et al. 2020, we already attempted to measure this with Keck MOSFIRE data only. So as shown in this top left table, this hints at the slightly enhanced equivalent width distribution from the UV brightest to galaxies compared to the faint bin. However, the measurement uncertainties are dominating the difference. Now, the clear data set, also including the Keck DEIMOS data set, we comprise the spectroscopic data set more than 200 galaxies at redshift of 6. So this allows us to constrain these quantities at higher confidence level. So in the table here, I'm showing the e-folding scale measured at different UV magnitude galaxy groups and also displayed in the right panel. So y-axis is the e-folding scale of the equivalent distribution, and x-axis is the galaxy UV magnitude. And black points are the low redshift measurement from Santos et al. And our measurements at redshift of 6 are shown as red dots. The highlight is that we see a marked enhancement from the brightest object compared to the faint object, so which is unlikely from the low redshift measurements. Finally, we estimate the Lyman-alpha transmission in the IGM at redshift of 6 based on these equivalent width measurements. So we define the relative IGM transmission, which is the observed equivalent width divided by the intrinsic equivalent width. As we do not know the intrinsic value, so we take equivalent width measurement from redshift below 6, where reionization nearly completed as the intrinsic properties. From this estimate, we can see that the transmission value are shown in the last column in this table. So you can see here the boosted IGM transmission to IGM from the brightest galaxies compared to the faint objects. So this indicates an inhomogeneous process of reionization with highly ionized IGM around the UV bright galaxies. And this is my summary, and I will take questions.
All right, thank you. So we have time for maybe a couple of quick questions if people want to put on Slack.
There's a question from Christopher. Is it possible to derive a statistical value of the Lyman-alpha escape fraction from the equivalent width e-folding?
It is ideally possible, I think. So you can estimate the Lyman-alpha photon production from the star formation rate from the entire galaxies. And we can derive the observed Lyman-alpha light from the observation. So I haven't tried that, but yeah, I think it's technically possible, and yeah, that would be interesting.
All right.
Yeah, we're probably out of time at this point.
Yeah, if there's no more questions, so we can continue other discussions on Slack, and let's thank all the speakers for this session.